looking at your textbook picture, think about what is it that all these different substances have in common. There's something that they all have the same. And what they all have that is the same is that they all have carbon in them. And that is the intro to our chapter on organic chemistry. Okay, chemistry. This chapter, organic chemistry, is, for better or for worse, very different than any chapter we've done so far. For some of you, that's good news. For some of you, it's like, oh no. But no worries. We're going to do just fine through this chapter. And the first thing we're going to have to identify is what is organic. Now, today we are more and more thinking that organic is something that is grown without using herbicides and pesticides and so forth. Well, that's not what this organic means. Organic means that the substance is made out of covalently bonded compounds that have carbon except carbonates and oxides. So baking soda is not included in an organic compound. That's sodium bicarbonate. Notice it has carbon in it, but no carbonates are included. It also does not include any oxides. So no carbon dioxide, no carbon monoxide. So you say, oh, there's a bunch of exceptions. No, that's only a few. So if it ends in carbonate, like calcium carbonate, that's lime, that's what makes the Lincoln Memorial, that is not considered an organic compound. If it has carbon dioxide, carbon monoxide, it's not organic either. Everything else is organic. I'm going to pull the camera over just a little bit here and try to show you. I have this huge book, very fat book, thick book, and it has so much information in it, constants and so forth. I just marked out from here to here is just on organic chemistry. The rest includes things still about organic chemistry and inorganic chemistry and physics and so forth. But this section alone is on organic chemistry. If you take organic chemistry in college, you will find that that is probably one of the fattest books you're going to get, one of the thickest books you're going to get. It has so much information in it. Carbon is one of the more amazing elements on the periodic table. And it's unique because carbon can form chains, rings, bind covalently to other elements, and to bind to itself and other elements in different arrangements. The sky is literally the limit. Think about it this way. How many words can you make using the English alphabet? There's 26 letters. How many words can you make? And if you think about it for a moment, you start to think, well, there really is no limit. In fact, which is a stronger password? A password that has numbers in it or a password that has letters in it? And a password with letters in it is much stronger because there's so many different options. Carbon is kind of that way. There is really no limit to the molecules that you can make with carbon. When you have finally made, let's say, a word that's longer, you can just add one more character and then you have all those options all over again. And it's the same way with carbon. So many options because it can bond so many different ways to so many different things. All right, let's start at the very beginning. Some vocab here. It says carbon atoms are unique in their ability to form long chains and rings covalently bonded atoms, that is, to itself. And this bonding is known as catenation. Covalently bonding of an element to itself to form chains or rings. And carbon does that very, very well. Now, carbon, if it bonds to itself and hydrogen only, we're going to call that a hydrocarbon. Hydro meaning hydrogen, carbon meaning carbon, and they are the simplest organic compounds. And again, really, just that alone, the options are virtually endless. Other compounds that have other elements in it, but can use hydrocarbon as a backbone. So here you can see this is all a hydrocarbon, and then we can add something like oxygen to it. And that could be oxygen, nitrogen, and sulfur, and the halogens. Those are the common ones that can be attached to carbon, again, forming an endless number of options. Now, before we dive into the next part, let's talk about carbon. You remember that carbon has, from our periodic table, it has 6 protons, and it has 4 valence electrons. So it would like it's got 4 electrons, and it would like to have 4 more to satisfy the octet rule. So you remember that if we were to draw the Lewis dot structure for carbon, we'd have 4 dots. So it would love to share its 4 electrons, and this is why it usually does things covalently bonding. In fact, I'd say always. And we can bond it to somebody else. Something like this. So carbon will form easily 4 single bonds. And it's these 4 bonds that it wants to make that make it so versatile, because it can form single bonds, it can form double bonds, it can form triple bonds, it can form them with many other elements, and so we have lots of options. We're going to start first by just focusing on carbon and hydrogen, because that gets us the simple hydrocarbons and some of the different combinations that are possible. So compounds that have the same molecular formula but different structures are called isomers. Now, a single carbon is pretty easy. There's really no other options for the way it can be bonded to hydrogen, and so it can go in this form. So we've got 4 carbons here, and this particular hydrocarbon is going to be called butane, and we can attach hydrogen all the way around it, and it takes forever to draw them. So this is butane, and here is a molecular model of it, and you'll see that even though I've drawn it straight, in reality it is not straight. And you might remember, because of the Vesper theory, everything wants to get as far apart from each other as possible. You'll see this tetrahedral geometry here on each carbon, and so it winds up being a little bit of zigzag, even though in chemistry we call this a straight chain. We'll talk about when it's not a straight chain, but this is a straight chain. And to keep things simple, I'm going to also show you one that does not have any carbons on it, because the carbons kind of the hydrogen's on it, because it kind of muddies up the waters. Now, we can connect them one after the other in this fashion, but there's also other options. So I'm going to draw it just with the carbons again, and what we can do is we can take one of our carbons and pull it off here and attach it to this carbon here. So this would be drawing it in this fashion: carbon, carbon, carbon. Here's our 3 carbons, 1, 2, 3. And then we could have one that comes off of here, like that. So now with this molecule, I'm going to take off one of these hydrogens and put this guy here. And now you can see this guy becomes this guy with all the hydrogens on it. Chemically, they have the same exact formula. They're both C4H4 8 9 10. And this is C4H10. So they have the same chemical formulas, but they don't have the same arrangements in space. One is like this, and one is straight. So do they get the same name? No, they can't have the same name. This kind of difference in structure, these are both isomers, and these are what we call structural isomers. Structural isomers. They have the same chemical formula, and they're connected to different carbons in the sequence. So on our next page, on 679, it points out 2 different kinds of formulas, structural formulas. Both are trying to show the exact same thing. This is called a plain old structural formula. Every atom is shown, every bond is shown. Even though the bonds are long, that's just because of the way the printers had to print it. They it doesn't make it any different than the shorter ones. They're all the same thing. Over here, this is called a condensed structural formula. We still show all the atoms, but we don't show all the bonds. So let's take our example right here of butane. How could I draw this with a condensed structural? This is a structural formula. Here's the condensed. You see I have a CH3, and then what do we have? We have a CH2, and we can show a bond in there. We don't always do that either. Then we've got another CH2, and then we have a CH3. So this formula and this formula are the same thing. This one is full structural. This is condensed. Now, let's talk about the name of these two. Again, this was butane. So we can't call this the exact same thing. So we're going to talk about how to name this. Right now, it's okay to just mention that its name is 2-methylpropane. We're going to talk about how this naming comes about, but just as a hint, the 2 talks about which carbon it's attached. 1, 2, 3. It's on the second carbon, so that's where that 2 comes from. And the methyl has to do with the name of this group, which we're going to talk about in a little bit. So there are 2 kinds of isomers. There's the kind that are structurally connected differently. And then on the next page, we're going to talk about another kind, but I need to touch bases on one other thing here. Here's a structural formula. Here's a condensed structural formula. Here is a condensed structural a structural formula, sort of condensed, but it's a structural formula. This is another way to represent the same molecule, and this is called ball and stick, which you get to do in your homework. So you can see here this carbon, here are the hydrogens, here's the OH, here's the OH, and we call that a ball and stick model. Then this is called the space filling model, because this is actually more likely what it actually looks like. Electrons spinning around and overlapping rather than being separated by sticks. But sticks is what we usually use because it's just easier to demonstrate it. I even have the model pieces that I could use it to look more like ball and stick, but they're pain in the neck to put together. Okay, back to isomers. On our last page of the section, 680, we talk about geometric isomers. It's the second kind of isomer. Now, as mentioned before, carbon can form a double bond. And in so doing, we can make a model like this where carbon is sharing two bonds, 4 electrons, 2, 4, 6, 8. 2, 4, 6, 8. Now, the difference between a double bond and a single bond, in this case, is that a single bond can rotate. And so it's not necessarily special whether the molecule is like this, or like this, or like this. Why? Because it can rotate. Whereas a double bond actually can't rotate. So that means that even though these are all attached the same way as this molecule, they're not the same. They have the same chemical formula, C2, 2 H's, and 2 chlorines, but they are not the same molecule. So we've come up with ways to name these two. When the molecules when it has the attached groups on the same side, that is called cis. When they're on opposite sides of the double bond, we call that trans. And I like to just take my hand and align it with the bond, and I look, okay, if the groups are on the same side of that double bond, that's what we call cis. If they're on opposite sides of the double bond, then that's called trans. And you're familiar with the word trans, like transatlantic, trans-Siberian railway, transportation. All it means is you're going from one thing to another, across, and that's what trans means, and this is cis. We're going to talk about that a lot more because it gets a lot more complicated. As you can see here, there's a molecule where you have this double bond here, and you have huge groups attached to each one. These two molecules are identical except for this double bond, and here you can see the trans one because it's on opposite sides of the double bond. Here it is on the same side, and so that's called cis, and you can see that's getting thrown right into the naming of the molecule. When it comes to drawing cis and trans, it matters a lot. So we're going to show it like this. Double bond to chlorine, hydrogen, hydrogen, chlorine. This is the trans version. And then we could do I like to start with a double bond and go from there. This is the cis version. It's very important to carefully draw that you've got these groups attached opposite or the same side. Now, when it comes to drawing this guy, it doesn't matter so much because we have a single bond, and since it can rotate, I could draw it with, and notice we draw it like the hydrogen's coming out to the end, but it isn't, but it's hard to draw it three-dimensionally here. So we can put the hydrogen here, we could put the chlorine here, and we could put the hydrogen over here. Now, I could put the chlorine down here, make it look like that. I could even put the chlorine over here. It actually doesn't matter. Why? Because this thing can rotate. So even though I could draw this one with a chlorine here and a chlorine here, it is no more a cis or trans than anything else because these two are the same. They're the same thing, even though I've got my chlorines drawn in different places. It's hard to remember that they're the same thing. They're not structurally different at all, while these guys are. All right, that's it for our section.